Okay, so today I want to go over quantum mechanics, right? I was toying around with the idea of just going straight into quantum field theory, but I figured for the sake of completion and for the sake of being able to have you understand these complex topics, we go back to basics, right? This isn't to bore you or anything, but this is just to sort of make sure that I can feel comfortable moving on to the more advanced stuff in quantum field theory. Because a part of me sort of felt wrong about skipping over almost everything in quantum mechanics and going straight into quantum field theory. I think the one or two lectures that I've posted already are still pretty good on sort of giving an intro, but I want to take a step back now and I want to go over the postulates of quantum mechanics. So the first postulate is goes like this: the state of a quantum system is completely specified by the function psi that depends on the coordinates of a particle. All right. So this is if I break down this sentence first, our initial picture was that we have some field, and the coordinates along the field are specified by psi and psi dot. This is sort of what we have been establishing, and this isn't wrong. This isn't like a wrong view or anything like that. This is somewhat of a new sort of original view, but it's not. It helps us sort of organize the idea of the difference between these states and the Lagrangian, which exists at each state, or for each state. Okay, so this was our picture that we've been developing, but I want to take a step back now, and I just want to look at this guy right here. So this wave function, it describes the state of a particle, right? Again, the field is sort of the state field or phase field, phases. So a particle doesn't travel from here to here per se. It travels, when it does travel between here and here, it's not traveling across space. It's traveling across states, right? Because the coordinates are described by states. And the state of a particle, as we said early on, is a function of 3 or 4 variables: t, x, y, and z. And then this guy right here is just a derivative, and it's still a function of t, x, y, and z. And together these make a point on this phase. So we need two values here: the position and the momentum, or perhaps and velocity, perhaps not momentum. The velocity of the states, to get an accurate picture of the dynamics that exists between the two states. Okay, but again, these are states, and this is what the first postulate says. This psi depends on the coordinates of the particle. These are the coordinates of the particle are these guys, the t, x, y, and z. So these are the coordinates of the particle. So what's basically saying is that you give me a position of where some particle is in three-dimensional space and where it is in time, and I could tell you what state that particle is in. And these are quantum states. These are kind of a quantum state. We do have to sort of step back and ask, well, what exactly is a quantum state? Well, this is exactly what this is trying to get at. A quantum state. A quantum state is a state that a particle is in, much like you or me might be in a happy, sad, or depressed, or excited state, and there's really nothing in between. A particle it sort of takes on these little values too, right? But we call them quantum states because there is no emotion in between. There's this is kind of what makes it quantum. The idea that we can assign some arbitrary quantum state to a particle is exactly why it's quantum in the first place. It's kind of assigning emotions to a particle, if you will, in which no other emotions exist between any two emotions. Right? Yeah, we might have happy and sad. The particle might be happy and sad, but there's no in between at all. But instead of happy and sad, this is sort of an arbitrary quantum state. Okay. And these states, again, depend on the particle's position, where it is in space, and where it is in time. Okay, so these are quantum state psi. And there's two ways we can represent this state. One way is in the Schrödinger view. The Schrödinger view is like this. The Dirac view, or the Dirac Formalism, is like this. Okay. Now the Dirac Formalism is particularly useful when we get into higher advanced stuff because this here is a function. This here is a function. So I'll just say this is a function. And this here is a vector. Okay. So when we say function, we're saying, again, this thing is like a function of t, x, y, and z. And this is Schrödinger's view. Ch. Schrödinger. This is Schrödinger's view of quantum. And then this here is a vector. So we could have something like this, perhaps. And this is Dirac's view. Now the link between these two, we can talk about the link between the function and the vector. And it's not the way I like to think about it. The link between the two is that functions and vectors are not all that dissimilar from one another. For example, you might have, this is what our function might look like just in 2 dimensions. So say we have a t and psi of t. Say it just depended on time. And our function maybe looks like a Gaussian. Like that. And the way I like to think about this is as we march along our independent axis, our independent variable axis, we add dimensions to our vector space. Okay. So in this case, we would have, if I were to actually just do it like this, I have 3 points, right here, and right here. We can sort of think of this function as something living in 3 dimensions, where we have, this is t1, our value at t1, this is our value at t2, this is our value at t3. Right? So at on the t1 axis, here's the t, I'll call this the t2 axis, and I'll call this the t3 axis. So on the t1 axis, our point is right here. It's not very large. On the t2 axis, it gets really large. And on the t3 axis, it again gets pretty small. So we have a volume now. We have a volume now that looks something like this. Actually. And the point here, from our origin to here, this is our vector. All right, so we've represented this function as a vector. And this is the idea of where Hilbert spaces come in, because a Hilbert space is a multi-dimensional vector space. So it's hard to visualize that, but we could see as we march along one of the axes, we can develop a vector that represents our function in multi-dimensional vector spaces. And these things, when we say vector space, we're implying that we could have something that has, we could start at 0, then we have psi 1, then we have psi 2, and we could go all the way down to psi n. And this thing behaves like a vector, even though we can't visualize it. It still behaves like a vector. We can still add it to other vectors. We can apply matrices to this vector, and so on. The only thing we've been stripped of is being able to actually just visualize it, and because our feeble little minds can only visualize in 3 dimensions. But again, nothing's stopping us from having this multi-dimensional Hilbert space that these quantum states can live in. Okay. So that is how that's sort of the link. This is the idea. This link right here is the link that takes us. Is this link right here that takes us from the function view to the vector view. Okay, so in this case here, here we have, this is a function of 4 independent variables. And so along the x-axis, this would be sort of along the x-axis, our value along the x-axis. This would be our value along the y-axis, and our value along the z-axis. Okay, and you can imagine as you sort of, if this were to change, this point right here were to change like this, and you have something like that, instead you have this little blip, then this value here would stretch up a little bit to right here, and our volume increased just a little bit. All right, I don't want to get too hung up on this, but there is a link between the function view, or the Schrödinger formalism, and the Dirac formalism, which is this vector view. The Dirac formalism is particularly useful because we can understand how we can operate on these guys when we begin to consider something like this, for example. So this is our state vector, and we want to expand this. So the way you would expand this actually would be a summation. Actually, you know what? I will do this over here. I'll do this over here. Here we go. So I have some state, and this can be expanded into its bases, its corresponding spaces that looks like, say I have my index. How do I want to do this? A, I, psi I, like that. So, and we're summing over I, this would look something like A1 psi 1 plus A2 psi 2, and I'll just go out to 2. So this vector here is expanded in its bases like a vector. So this is like a vector. So along the psi 1 direction, we have this weighting. Along the psi 2 direction, we have this weighting. Using 1, 2, 3, 4, and 5 is, in some sense, better than using t, x, y, and z because we have more numbers at our disposal than letters in the alphabet. So this allows us to do something like this in a Hilbert space. So again, this is a vector that exists in some Hilbert space, and we sort of summarize the notation like this. Similarly, we have these objects. So this object here is a vector. It lives in this space, this vector space. We could entertain the idea of a covector. Now this doesn't really implied yet in this first sentence of the postulate, the first postulate. They said they call this a wave function or safe function, and it has a property that this is the probability that a particle that lives in the volume dt. Well, the probability, that's a number. That's something you can actually measure. So we want to be able to apply something to this vector such that we can get a number out of it. And this is where the useful idea of the dual space comes into play. So this is the space, or the vector space. I'll call this the vector space. Vector space. And this is the dual vector space. And the way we represent that is a function like this. This is the bra vector. Or no, this is the ket vector. This is the bra vector. And this is expanded to look like, you might have guessed it, like this. And we have weightings on our dual vector space. And again, it's expanded out like this, and we're summing over I. All right, so we have this vector space that describes our vector, or that describes our state. And we have this dual vector space such that if we were to do this, this is something we can actually measure. The probability. So this is a number. This is a complex number. This is in the complex numbers. And then if we were to square it, this is our probability amplitude. So this is our probability. And this is our probability amplitude, which brings us into the reals, because squaring anything with an I in it, you'll find that anything that has an I in it, I times I, so I squared, is just going to give us -1, and that automatically puts us into the reals, and so this is the probability amplitude. And so, with this in mind, what about, looks like I forgot this. With this in mind, we can talk about something very interesting actually. So this here is this is like an inner product. This gives us some number. All right, so when we apply the dual vector space to the vector space, to an item in the vector space, then we get some number. But we could do it in the opposite order. We could do something like this, in which case this is not part of the complex numbers. This is not part of the complex numbers. This is actually an operator. So this is an operator. And when the two states are the same, have the same sort of quantum value to it, or the quantum, this is psi and psi are the same. So this is the identity operator. And we could prove this to ourselves. And by doing that, I'll show you. If we wanted to build an operator, we could do something that looks like this. So this is our operator T, and these are my two states, like this. And they're being applied in a way that will give us an operator. And let's prove this to ourselves. So we set this equal to, let's see here, it's going to be the sum over I and j, and we want to put a weighting on our alphas, and then we want to put a weighting on our, I'll do it like this actually, just to make things a little less confusing. I'll just put an I right here. This is our basis for the alpha states, and this is going to be our basis for the beta states, and then it's going to be beta j. So these are the two weightings right here. This we can bring, these two things are just numbers, a, alpha, and beta. So we can bring that out. Alpha I j I j, like that. Okay. So this here is, so this is like a weighting on these, these are kind of like matrices almost, if you will. These are the operators right here. And this here is going to have two indices. We're summing over I and j, because this side has two indices to it. So we've sort of shown now that this thing is an operator, because these are just weightings, but then these are the sort of the basis operators that we build. Okay. And so we can play around with this notation. This is why Dirac's notation is so useful. We can play around with this notation. We could say that j alpha, for example. Say we wanted to look at j alpha. Well, we would just do, if j was the basis, we could do something like this, where we have a alpha I, we're summing over i's, like that. So again, this is a vector, and we're expanding it in its space, and then this is a vector, a unit vector, if you will. Usually I, j, and k's are unit vectors. And so if we just apply it like this here is on this side, on the left side of I. We can bring this into our summation. We can bring this into our summation, and we get alpha I, and then we want our j I, like that. This ends up being a Kronecker delta. So this is sort of the next point here. This is our Kronecker delta if we propose that the vector space is orthogonal to our vector. So every basis in this space is orthogonal to this space. And this is kind of like the idea when we were talking about GR too. When we made the claim that E mu and E mu, I'll call that nu, equaled the Kronecker delta. Like that. So if we say that the two spaces themselves are orthogonal, the two spaces, which mean the two spaces are orthogonal, so the bases of each one has to be orthogonal to the bases of the other. In other words, non-overlapping. Then we could say that this is equal to, this is just equal to AJ, or alpha J. Okay, because this will only be 1 if I is equal to J. So this here again, this gives us a number. This gives us a number, which is complex. Usually in quantum, we're looking at complex inner products that lead us to complex numbers. And GR, we're looking for inner products that lead us to reals. And again, there's also nothing stopping us from inner products perhaps leading us to octonions or something like that, but we're not going to quite go into that yet. We're just right now looking at the first postulate of quantum mechanics, and I'm beating up this postulate I don't know. Let's go back to the postulate really quick. So this is called the wave function, and it has probability. So this is a probability that the particle lives in the volume dt. Okay, this is kind of like a volume, some sort of a little volume element, because each one is multidimensional, or you could think of it as an area element that lives in a little volume dt. And this is sort of, so we've come to a point. We've come to a point now where we can understand what it actually means, what this actually is now, what this object actually is, in terms of the Schrodinger state, and but mostly in terms of the Dirac state. I'll go back to the Schrodinger state really quick, because they're saying this here is a probability. This is part of the real, or this is part of the complex numbers. This guy right here is akin to doing something like this. This is just the Schrodinger view. Okay. Squaring them puts us into the reals. Squaring them puts us into the reals. And those are actual things we can measure. So these guys are put into the reals when we square them. So when we don't square them, we put them into the complex numbers, and when we square them, we put them into the reals. And there's actually there's an interesting philosophy behind that, right? The idea of using complex numbers in the first place. The idea of using complex numbers in the first place is a very interesting one, because probability theory, we won't go deep into probability theory, but the idea of squaring something to get something measurable out. If you remember from GR, if you remember from what we've gone over so far in GR, the idea that we square something, that's the square is the relevant thing. The square of the object, if you remember, ds squared equals dx1 squared plus dx2 squared. These are all squared. There's something to this squaring that makes life possible, right? There's something to the squaring that renders it important to some degree. So this goes, so you could see here that the square of the states is a thing, and this bodes well with complex numbers, because when we square a complex number, I squared, this brings us into the real numbers. So it's not just that or complex numbers in general are, it's not just that complex numbers in general are just interesting things to look at, but squaring them, it sort of falls in line with this Pythagorean notion. So, and if you remember in GR, this was equal to GI J with the bases on it, I, E, J. This guy here, when we take the square root of that, right, that's going to give us our ds. Right, but so this standing alone, ij, gives us something it gives us some information about ds squared. This is why the metric tensor is so important. Okay, this is why, and so with that being said, I don't know how long I'm going here, because part of my computer isn't working and it's not telling me the time. But I think we've beaten up this postulate enough. We can come to understand now what exactly a state is, how exactly we can work with it, and how exactly it's linked to the Schrodinger view. Okay, so I think we've beaten up this first postulate enough, and we'll go into the next postulate in the next video, or I might make another biophysics video. We'll see. But I hope this helps in getting us started to dive into quantum field theory, and even some quantum mechanics probably. Again, I'm on no time crunch. This is kind of like a project to me, and I enjoy doing this kind of stuff because teaching is it's sort of in my blood. So with that being said, I will see you guys in the next one. Thanks.